Great. So today we're going to finish off talking about boosting, in particular about data boost, and then we'll talk about, we'll start talking about margins, geometric margins, and in particular I'll focus on perceptron, and if I have time I'll start talking about kernels, and next time we'll do SVM. And actually all these topics have something nice in common. They are all widely used in practice, but also backed up by solid foundations. Okay, so that's one nice thing I like about these topics. Great, so just a very quick recap. So we discussed about this last time. So what is boosting? It's a general method for improving the accuracy of any given learning algorithm, and at a high level it works by creating a series of challenge data sets such that even modest performance on these data sets can be then used to produce an overall highly accurate predictor. Okay, and we discussed this in detail last time, and we also discussed AdaBoost, which is an algorithm that is widely used in practice and also has been thoroughly analyzed from a formal point of view. And in particular, last time we went through the analysis of the showing that the training error of AdaBoost goes quickly to 0 as you increase the number of rounds of boosting. Okay, but I also want to talk about generalization guarantees because the story here is particularly interesting. Okay, so just a quick recap what AdaBoost does. So well, it's a boosting procedure, and in particular, what AdaBoost does takes as input a training set of examples, so this is a set of labeled examples, right? So this is xi here is the feature part of our examples, and this is a label part, y is a label part, right? So the input of the algorithm is a fixed set of training examples, and also a weak learning algorithm. Yeah, so we also have as input a procedure, an algorithm that is able to produce weak learners or rules of thumb. Right? So this could be, for example, naive Bayes, or it could be some procedure that produces decision stumps, which are very simple classifiers. Okay, so the input to the algorithm is basically a set of training examples, labeled examples, and a weak learning procedure. And then the output of the algorithm should somehow be a very accurate classifier, right? As accurate as you want it to be. Okay, and so to do so, what AdaBoost does, it proceeds in rounds. In each round, we have a distribution dt over the training set of examples. And in each round, we run our weak learning algorithm on this distribution dt in order to get a weak classifier ht. Okay, and then we use this weak classifier ht to then come up with and the underlying distribution dt in order to come up with a new distribution, a new challenge distribution for the next round with a distribution dt plus 1. Okay, and we went through this in detail last time. I'm just gonna, so I mean the specific, right, and the AdaBoost has a specific update basically, so it has a specific way to come up with distribution dt plus 1, and we discussed this last time. So this is the formula here, but really what AdaBoost does, so it's very simple what it does. So the way you create a new distribution dt plus 1 is simply by increasing the weight on the incorrectly classified examples by the current weak learner, and by decreasing we increase the weight on the incorrectly classified examples and decrease the weight on the correctly classified examples, right? So I'm somehow trying to focus on harder examples. And more concretely, the way it does it, so it will gonna, right, so if an example is incorrectly classified, then we increase its weight multiplicatively by e to the alpha t, or alpha t is appropriately chosen as a function of the error rate of the classifier ht. And if it's correctly classified, we decrease its weight with the same factor. Okay? And right, and this is the update rule. The easy way to remember it is just basically all we do, we create a new distribution dt plus 1 that has the property that has exactly half of the weight on the examples on which the previous classifier ht was incorrect, and exactly half of the weight on the examples on which the previous classifier ht was correct. Okay, so it's very easy to remember. And that's pretty much the algorithm, right? And then we go for a number of rounds, and then we just output a classifier which is a weighted majority vote of the weak learners we've generated so far, right? And the strength of the vote also depends on this normalization, on this factor alpha t that was also used in the updates, right? And so basically, the more correct, the higher the error rate of the hypothesis ht. Sorry, the higher the accuracy of the weak learner ht, the higher the weight in the final classifier that weak learner will have. Okay, but in any case, okay, good. So that's the ADA boost. It's very, very simple. We just proceed in round. In each round, we have a current distribution over the set of training samples. We run our weak learning algorithm. We get a weak classifier. And then we use that weak classifier and the current distribution to come up with a new challenge distribution by simply making sure that under the distribution dt plus 1, we have half of the weight on the examples on which the current weak learner is incorrect and half of the weight on the examples on which the current weak learner is correct. Okay, and then we combine, at the end of the day, all the weak learners generated in a majority vote, weighted majority vote. Okay, and then we want, so as you guys can see, as we discussed this, the algorithm is really simple. It's easy to code. It has no parameter to tune. It's very fast, and it's also very general. We can use, as a black box, any of our favorite simple algorithms. Yeah?
Can you tell the reason behind taking half and half and not?
Yeah, so I discussed this last time. So the reason was a little bit technical. So, right, okay, I guess the reason was, okay, so I guess I don't have the slide. Let me see if I can recover. So the reason is basically, when you analyze the training error rate, we argue that the training error rate actually, let me see if I can use mine. Maybe I can do this. Right, so first of all, okay, so I guess, so last time we discussed, for example, several reasons. Okay, why not, I guess we already went through this, why not put all the weight, right, in dt, under dt plus 1, why not put all the weight on the examples on which ht is incorrect, right? We discussed this, and the answer is?
It won't learn.
If we do so, then it might not give anything new to us, right? Because it can always, if we put all the weight on the examples on which ht was incorrect, the weak learner will give us back the opposite of HT, will learn no new information, okay? So we cannot do something so aggressive, right? So then somehow we have to mix a little bit. We have to give under dt plus 1 examples on which the current classifier is correct and incorrect. We want to, though, nonetheless have significant fraction on the incorrect ones. Now, why did we put half and half? Well, because actually when we went through the analysis, maybe I'll do it here. So when we went through the analysis, good. So we noticed that the number of misclassification, or the error rate, the empirical error rate of ADA boost, right? So the empirical error of the final classifier, we notice that is upper bounded by m times the product of the normalization factors, right? So if we go back here, we have to create this distribution dt plus 1, as we said, we increase the weight on the incorrectly classified examples in this multiplicative fashion. We decrease the weight on the correctly classified examples, but then we have to renormalize, right? So zt is a normalization factor that makes sure that everything sums up to 1, right? And we went through the analysis last time, and we concluded by doing an analysis that the empirical error rate of the final classifier is upper bounded by m times the product of the normalization factors. Now, in order to make sure that we want this to decrease as quickly as possible, right? We want to drive this to 0 as soon as we can. And the analysis showed us when we computed the normalization factors that if we construct the distribution dt plus 1 in the way where we put half of the weight on the correctly classified examples by HT and half of the weight on the incorrectly classified examples by HT, we're going to get that this is when this will going to go as quickly to 0 as possible. So for that choice of the way to construct the distribution dt plus 1, this upper bound on the error rate goes to 0 as quickly as possible. Yeah?
So our task would be to get the lowest rate or the fastest rate to 0?
The fastest rate, the fastest decrease, right? So actually, let me actually go to the next slide. So as we argued, right, so we went through this proof actually, right? So in order we proved last time, right, that basically the empirical error rate of the final classifier decreases exponentially fast. So if gamma, so let's say gamma t is the edge of a random guessing of the classifier HT in round t, right? Then we argued that we want to prove this, that the empirical error rate of the final classifier is upper bound by e to the minus 2 sum over t of gamma t squared, right? And if all gamma t's are lower bounded by a single fixed constant gamma, that can be simplified to look like this, right? And actually, the way we proved this is, right, we had as an intermediate step, we argued that the empirical error rate of the final classifier is upper bounded by this product of the normalization factors. And for that choice of the way of the update, we got the fastest decrease. So it's a technical reason. But it's not hard, because we did everything in one lecture. Yes?
Could you give some intuition as to why this doesn't overfit much? Because one would think because you're training on different subsets of the samples again and again, it's more tuned to the training set. But on the contrary, last class there was a statement made that it doesn't generally overfit the data.
Okay, so that's exactly what I want to talk about today. Okay, so right, so this is what. Okay, so we went formally. right? And we proved last time this a statement about the empirical error rate of the final classifier output by ADA boost after T rounds, right? And so we argued basically that after T rounds of boosting, the empirical error rate is upper bounded by e to the minus 2 gamma squared t, so decreases exponentially fast, right? Which then basically, right? So for example, if you want this to be, what do I mean by decreases exponentially fast? Well, for example, if I want to set the empirical error rate to be epsilon, then if you go and compute, we only need to see 1 over gamma squared. We only need to do 1 over gamma squared times log over epsilon rounds of boosting, okay, to achieve empirical error rate almost epsilon. So that's very, very fast. Okay, if gamma is the constant, that's only log over epsilon rounds, so that's great. Okay, and but that's all about the empirical error. Okay, so to go back to your question, how about the generalization error? Yeah, because we always care about the generalization error. Okay, and here the story is really interesting, actually. Good. So how about the generalization error? Okay, great. So, well, so we've spent a number of lectures talking about how we approach trying to prove generalization guarantees for our algorithms, right, by using VC dimension-based bounds. Okay, and so we kind of know how to go ahead and attack this question. Okay, and so this is actually in their original paper, in their seminal paper, you have Front and Rob Shapir. I mean, obviously, they also ask the question not only analyze the empirical error rate of the final classifier output by ADA boost, but they also cared about the generalization error, about overfitting. Yeah, and the original approach in this paper was to basically use classic VC dimension-based bounds. Okay, and they did come up with a generalization guarantee, right, based on VC dimension of the following form. Okay, so. So to be concrete, let's assume that the weak learners that we find come from some hypothesis space H, right? It could be the class of decision stumps, or it can be some other simple type of classifier, okay? And let's assume that D is a VC dimension of this class of weak learners, okay? Now, we know that we just went for the algorithm, but we know that the final classifier output by ADA boost is a weighted majority vote of these weak learners. Basically, it's a weighted majority vote of T weak learners, right? So we let them vote, and then we just threshold the vote. Okay, this is how the final classifier looks like. And now, based just on this observation, then they immediately, you have and Rob, they immediately came up with a generalization guarantee by simply coming up with a generalization guarantee for uniform convergence bound for this class of functions. Yeah, that contains the final classifier output by ADA boost. Okay, so in particular, they showed that basically they had this uniform convergence bound that holds for any classifier that is from this class of functions, which basically is the class weighted majority votes of base classifiers, of T-based classifiers, right? And so it's actually, you can then show that uniformly for all functions in that class, we have the true error is upper bounded by the empirical error times some complexity plus some complexity term, plus whatever depends on the complexity of this class of functions. But, and this will, I mean, this, we should have here the VC dimension of this concept class, of this class G, square root of the VC dimension of this class G over M, right? This is how a normal generalization bound would look like. Right, so basically all we have to do is to compute the VC dimension of this concept class, right, of weighted majority votes of T weak learners. Okay, and it's not hard to compute. You can show that if we let T weak learners vote, then the VC dimension here is up to log factors D times T, where D is the VC dimension of the base class. Okay, and I'm not going to go through this. I just want to mention that basically the proof is not hard. I mean, I think in your homework number 5, you had a question about computing the VC dimension of the intersection of two concept classes, right? And then you looked at the shattering coefficient and so on. You can use a very similar reasoning to then argue that the VC dimension of this class of weighted majority votes of T weak learners is basically D times T times log D. Okay? So by just using a reasoning of this type and the standard generalization bound, you can come up with this generalization guarantee this uniform convergence bound for all classifiers in this class, and so then basically would also apply to the classifier output by ADA boost. Okay, But now, of course, if we think about this bound, and if we think about our favorite picture, as we've seen in lecture number 1, and then in the learning theory lecture 2, right? So, I mean, what do we expect? We expect the following to happen, right? We expect that as we increase the number of rounds of boosting, right, we have a more and more complex classifier, and we expect that the training error is going to go to 0, right? Now, we also know that, by just analyzing the bound, and also intuitively makes a lot of sense, we also know that as we increase the complexity of the classifier without other boost outputs, so in other words, as we increase the number of rounds, right, we know that, so the behavior should look like this, right? So originally, basically, the generalization error is going to go down, but at some point, basically, the second complexity term we're going to start dominating, right? And then we'll start overfitting, right? So this is what we expect to happen. Right, so there will be a sweet spot, but after that sweet spot, now the complexity term are going to start, the classifiers become way too complex, and this term we're going to start dominating, and so then we might expect that we start overfitting. Okay, this is what we expect. So I guess, is this answering your question? Just to make sure, in order to understand the generalization abilities of AdaBoost, what we have to think about is we have to think about the complexity of the class of functions that AdaBoost outputs, right? And we have to reason about that complexity and use our our standard tools, yeah? Okay, so if we do so, then we'll expect to have this picture. However, yeah?
So can we say that after, as the number of rounds increases, we have overfitting?
This is what you'd expect, okay?
Yeah.
But here is the cool fact. It turns out that actually this is what everyone expected, right? So, but it turns out that actually experiments with boosting showed that the test error of the generated classifier, so the test error of the classifier output by AdaBoost, somehow did not increase as the size of the classifier became very large. And in fact, something very puzzling happened. It turned out that, so somehow even after, so it turned out that even after, so for example, there are experiments, and so this is, for example, a picture from the letters data set. So in this data set, for example, after 5 rounds of boosting, the empirical error rate already reaches 0. Right? And obviously, if we keep increasing the complexity, the empirical error rate only, cannot go below 0, but stays 0, obviously, right? But interestingly, the generalization error kept going down. Right? So basically, experiments with boosting show that continuing to add new weak learners, even after correct classification of the training set had been achieved, could further improve the tested performance, which really contradicts the picture that we had on the previous slide and what you'd think about intuitively. Yes?
What's M?
M?
Yeah.
M is the number of training samples. Okay. Yeah? So when I described AdaBoost, I said I have an input and a set of training examples of size M. A fixed, yeah? So it's the number of training samples. I think we consistently use M as a number of training samples. Yeah, in any case, it's a number of training samples. Yeah. Of course, please ask questions, to make sure that we are on the same page. Okay, cool. Basically, right, experiments with boosting show that basically, even if we keep adding weak learners, even after perfect classification has been achieved, somehow the generalization error keeps going down, so the test error keeps going down, which seems to contradict this type of generalization bound, and also the more basic Occam's principle, which says that in order to achieve good test error, the classifier that we output should be as simple as possible. Okay, so this is like totally surprising, puzzling. How can that be true? Okay, that was not only on one data set, it was consistently observed on many data sets. Okay, so obviously, when people have tried to understand that also at a more formal level, and there was a very nice work by Rob Shapiro, Affron, Peter Bartlett, and Winston Lee that came up with a very interesting explanation. Okay, so basically the key point that they made is that the training error does not tell us the whole story, and we also have to consider somehow the classification confidence of the final classifier. Okay? And let me be a little bit more concrete here, right? So, okay, I'll be here intuitive, I'll stay at a high level and then become concrete in the next slide. Okay, so the whole point is that, right, so we should care not only about the classification error, right, about the the training error, but we should also care about how confident is the classifier that we output on most of the examples. And it turned out that somehow as we increase the number of rounds of boosting, the final classifier became more and more confident on its predictions on more and more examples. So in other words, the margin increased. Its margin on most training examples kept increasing. So for example, right, as we had more and more rounds of boosting, right, we see the bold one is after more and more rounds, somehow the final classifier is more and more confident on more and more examples. Okay, and so, yeah?
How do we measure confidence?
Exactly, perfect. Okay, so here's my slide. Okay, so this is the formalization, but actually let me just jump to the wordy explanation. So the confidence, so we have a final classifier, which is basically, it's a weighted, so the final classifier is it's a weighted majority vote that we event threshold, right? So let's assume that the final classifier is given by a weighted majority vote of T-based learners that we event threshold, right? So now, and we can think about alpha T as the confidence that we have in the weak learner HT. Right, the weight we have, we put on the weak learner HT. Then we can define the confidence or the margin that the final classifier has on an example X as basically as a weight on the weak learners that agree with the true label minus the weight on the weak learners that disagree with the true label. Okay, so that's basically what the confidence or the margin is. The total amount of weight I have on the weak learners that are correct minus the total amount of weight that I have on the weak learners that are incorrect. It's very natural, right? Notion of margin, right? And ideally, so right, and actually I will also do this after we normalize everything. So we also have to normalize everything so all these weights, I can always assume, because it's a linear combination of weak learners, I can always renormalize things so that it's actually a convex combination. So basically the sum of the weights sum up to 1. I can always do that, right? Right, and so this notion of margin is after this normalization, right? So after I renormalize the sum of the weights to sum up to 1, the margin is basically the amount of weight I have on the classifiers on the weak learners that agree with the true label minus the amount of weight I have on the weak learners that disagree with the true label, right? And if after I do this normalization of the sum of the weights to be 1, then basically this confidence or margin, you can argue it's in between -1 and 1, right? If it's 1, that means my classifier has high confidence and it's entirely correct. Okay, if it's 0, it means has very low confidence, right? So this basically this sum, right? So this sum here that I need to threshold and to buy y minus 1 or -1 is close to 0, so I'm very not confident, right? If it's -1, that means I have high confidence, but I'm highly incorrect too. Yeah. So that's the formal notion of confidence or margin that you use when you do when they use when they analyze boosting. Okay, and with this notion of margin or confidence, right? And actually, this is just the margin on example X. Okay, so anyway, I'm going to skip this. This will become a bit relevant later, but let's think about this intuitive definition here. Yeah. Good. So now with this notion of confidence or margin, what I guess Yuval Frond, Rob Shapir, Peter Barrett, and Wissam Lee were able to show is this following interesting results. So they were able to show that basically, so if a generalization guarantee that somehow does not depend on the number of rounds of boosting and depends entirely just on the margin and on the complexity of the class of weak learners. Okay, so more formally, right, so we are able to show that if the this dimension here is the this dimension of the class of base learners, which typically we think about as being very small, then we can show that basically this uniform convergence result quantifying the true error rate, so this is the true error rate of a classifier from the class of functions value output as a function of the margin, empirical margin over the training sample, plus a complexity term that depends entirely just on the VC dimension of the base class and has no dependence on the number of weak learners. Okay, and this can then be used to explain this type of picture, right? Because if I increase the number of rounds, if my margin keeps increasing, then that's great, because that means the classifier that I output is simple in a different form, in a different way. So it's not all about the size, is not all about the number of weak learners, but there is a different notion of complexity which has to do with how large of a margin the final classifier beta output has. So it's a different notion of simplicity. Yeah?
How does the boosting work after the training set is completely correctly classified? Because then you can't place half, well, what does it mean to place half the weight on the incorrectly classified example?
Well, if it's correctly classified, you stop, right? Actually, technically, if you go back, so there is no need to continue. Actually, if I go back, then the weight will become alpha t will become infinity. Because if you remember, it was log minus of 1 minus epsilon t over epsilon t, that would be log of infinity. Yeah, so it's stop. You should stop, right? If you notice, because you can compute epsilon t, actually even to make your update, to come up with your update, to compute your update, to compute alpha t, by how much you increase the weight or decrease the weight, you need to compute the empirical error. And if you notice the training error is 0, you could, oh, I see in this example, I see you are saying here. Oh, I see, that's a good question, actually, I see. So here you are saying, oh, yeah, but okay, so it could be that it's correctly classified, but not because the weak learner is perfect. So probably in this example, it was correct, the training sample was correctly classified, but not because HT, right? Okay, so right, so you can just continue. Okay, so as long as the weak learner doesn't have empirical error rate 0, you can keep, right, the weights alpha t are still bounded, and you can keep adding weak learners to your classifier. Yeah. I mean, so you basically you could achieve 0 training error after 5 rounds, but not because there is one of them that is perfect, but because the convex combination of those is good. Okay, so that's the reason, right? I mean, it would be a problem if one of them is perfect, because then the weight will become infinity, and that's not good. But actually, probably in these experiments, none of the weak learners was good. It's just that somehow the weighted convex combination was good.
And the alpha is only based on the most recent.
Exactly, alpha is only based on the last classifier. It's based on the error rate of the last classifier, the last weak learner. Not classifier, weak learner. Okay, this is a great question, actually. What's your name?
Ronald.
Ronald. Oh, yeah, okay, good. Great. So, okay, so bound of this type basically explains this type of behavior, so which is very nice, because when we have found theory that confirms practice, so it's good. We know that something meaningful happens. Okay, and I'm not going to go through the proof here because it's actually a non-trivial proof, but I just want to mention intuitively, very high level, how the argument would go. So basically, and this is the argument from the original proof that the original paper had by Front, Shapir, Bartlett, and Winston Lee. Okay, so here the high-level idea was basically to just notice that if all the training samples have large margins, then that means that we can approximate the final classifier by a much smaller classifier, by somehow using some sort of sampling argument. Okay, so okay, and then right, if we can then approximate the final classifier by a much smaller classifier, then we can argue that basically that implies that better margin leads to smaller test error, regardless of the number of weak classifiers. Okay, so that's kind of the very, very high-level intuition of the proof, original proof. I'm happy to present it to you offline. And I also want to mention that there is these days we know, so the original proof was based on first principles, but these days we know alternative proofs based on Rademacher complexity, which is a notion we covered when we did learning theory. Okay, so. But actually, I think the original one is a little bit more intuitive. So if you are curious, you should think about the original one. Okay, and I also just want to mention that in their paper, they also mentioned that actually they kind of have some sort of argument claiming that boosting AdaBoost tends to increase the margins by somehow focusing on examples that in each round by focusing on examples that have smaller margin. Okay, they also made an argument of this type. And so when putting all this together, then somehow the high levels, the punchline here is that even if, as we increase the number of rounds, somehow even if the final classifier is getting larger, the margins are likely to be increasing. So the final classifier is actually getting simpler, is actually getting closer to being a simpler classifier, which then explains why the generalization are going to keep dropping. Okay, so basically, margin is another notion of simplicity, essentially. It's not only about the number of weak learners, but the margin can capture simplicity in a different way. Okay, and then we can understand these empirical findings. Great. And everything is consistent. Cool, so just, so this is all I wanted to talk about AdaBoost. Did I answer your questions earlier about how to think about generalization error? So, okay, so formally, right, so formally here, how the margin relates to simplicity. I guess, so formally you can show, I didn't go through the argument, but okay, I guess, informally I did say that actually if you somehow find a classifier that has a large margin on most examples, then you can argue that it's approximated by a much simpler classifier. You can argue that. So in other words, another way to say it, and actually you're going to see another notion of margin soon, which is even more intuitive. So the next part of the lecture is about a different notion of margin, but intuitively speaking is, okay, to rephrase in another intuitive way is, well, there cannot be too many classifiers that are very different, that have a very large margin. So that's another way to think about it. Yeah? I mean, and also formally you can see it, so the bound here, this formal bound basically shows that the empirical error rate depends only on kind of the margin, the margin over the training sample plus some complexity term that does not depend on the number of weak learners. Okay, but really, that's so right. We are asking how is margin related to simplicity. Right, so the key maybe piece of intuition is to, if you have a classifier that has a large margin on most examples, somehow you can approximate it by a much simpler classifier. And now, how can you approximate in that sense? But depends on the specifics of the margin. Right, and here actually I had a specific notion of margin, namely this, if I go back here, it was this very specific margin, right, that I talked about in the context of ADA boost. Is why I'm thinking, like when I mention margin, I first renormalize all the weights to sum up to 1, and then I'm saying, well, the margin of an example is exactly the weight that I have on the weak learners that agree with the true label minus the weight that I have on the learners that disagree with the true label. Okay, so there are various notions of margins, by the way. Okay, and actually this perfectly motivates my next topic. Okay, yeah.
Go back to that sentences.
Which one?
You mean the smaller, use smaller classification, like for the decision tree, like we can pruning the decision tree to smaller, use smaller fewer features to can provide larger margin for decision tree.
Well, it's okay. So it's not clear that if you prune the decision tree, you're going to get larger margin. I mean, it's not obvious a priori. It could be that you have a smart pruning procedure that does that. But it's not. I don't think that all pruning procedures are going to lead to large margin. Okay, but it's a good question to think about. Okay, cool. So, any more questions about this? So actually, so to answer your question, the next topic will be about geometric margin perceptron, and then I'm going to go for a proof, and I'll totally convince you that in that case the margin is relevant. Okay, I knew that you guys are all curious, so that's why I decided to actually talk about it. I mean, I would also be curious, why suddenly margin makes things much easier, right? Oh, fine. Good. All right, but let me just sum up ADA boost and boosting here, right? So basically, so I think this is a very interesting paradigm. The high level is very different from the other types of learning algorithms we've been talking about, where like logistic regression or naive Bayes or some other learning algorithms are trying in one shot to get very small error rate, right? Boosting is different. Now we have a shift in mindset. Now our goal is just to find classifiers that do better random guessing, and then we have a wrap-up procedure or meta procedure that uses such a classifier to then achieve arbitrarily small error rate, right? So it's kind of very interesting, and the algorithms developed within this paradigm not only have very nice foundations, but they have been also very practical. Okay, and they have been used in all sorts of applications, from speech to vision to, I mean, basically any type of application. And actually, Willy, our TA who will do the next recitation, we're going to talk about this more in recitation. Okay, and actually, I would just want to mention actually that turns out that boosting some of these techniques actually have, I mean, many years after have other unexpected implications. So, for example, they have also in my own work I used ADA boost for coming up with communication efficient algorithms in the case of distributed learning. So now where the data is distributed across multiple sites and you want to do learning over the union of the data sets by using as little communication as possible. And intuitively speaking, it turns out that boosting techniques are really relevant because somehow they are designed to quickly focus on core difficulties or core parts of the data, which is exactly all we need to communicate. So if we want communication efficient algorithms, we can use boosting type of ideas to somehow quickly focus on the relevant parts that we should communicate with the other parties. Okay, so it's kind of interesting that it had many other implications. Great, so I guess this finishes the discussion of boosting. So any more questions or comments? Okay, cool. Then I'll go to the next topic. Right, so actually, I decided to talk about, for the next topic, I decided to talk about the perceptron algorithm, which is one of the simplest algorithms in machine learning. It's from late 50s, and the reason for which I decided to talk about it is exactly because it's the simplest case where you can just understand why the margin is so important, right? So the original analysis actually was based on the notion of a geometric margin, and somehow showed that the mistake bound or the generalization guarantees of perceptron depend on the margin. Okay, and this dates back to 50s, so it's kind of interesting. And also another nice feature, actually, the original algorithm was in the online learning scenario, and I had a question last time about what online learning means. Okay, and so I thought I could take the next topic to be about perceptron, because I can touch both on online learning and a different notion of margin and make it even more apparent why margin is so important. Okay, cool. So now, right, so I'm going to talk about the perceptron algorithm, describe it in the online learning model, present in detail the notion of geometric margin, and then I'm probably not going to have time, but next time we're going to take it from there and talk about kernels. Actually, perceptron is also a very good algorithm for describing another very important paradigm in machine learning, namely kernels. So I think the simplest way to introduce kernels. Okay, great. So now we're going to, so far in the course, so I'm going to start talking about perceptron, right? And so far in the course, we mostly have been talking about the batch learning scenario, right? Where we assume that the data is all given to us up front, right? So we're trying to classify maybe spam or we're trying to classify emails or images and so on, and somehow imagine that we have a lot of the data given to us up front. Okay? Now here is a different paradigm where this is called the online learning model, where the examples arrive sequentially, one at a time. So each day an example arrives, like an email arrives, and we need to make a prediction on that example, and then at the end of the day we get to observe the outcome. Okay, so pictorially, right, so we're going to go for a number of rounds, potentially many rounds, many phases. In phase I, first an example xi comes in, so an example xi appears, right, an email, for example, appears, and I must make a prediction immediately, right? And then I'm told the true label of that example, right? And then I can use that information to then update the internal state of the algorithm. Okay, so that's the online learning scenario, basically. So it's a sequential model, right, where examples arrive sequentially. In each, we go for a number of rounds. In each round, first an example appears, an example xi comes in. We have to label it, right? We have to make a prediction immediately. Then after, if we are correct, it's great. If not, we're going to incur a mistake. We're going to make one error, right? And then at the end of the day, we get to observe the true label. And then we can update our internal state, obviously, to somehow use that information that we learned to do better predictions in the future. Okay, so that's the online learning model. And traditionally, actually, in the original traditional model, actually, we're no longer even make distributional assumptions. So, right, so throughout the course, we assume that the data comes from some fixed but unknown distribution. We make distributional assumptions. Now, in the online learning model, in the extreme case, we think about worst case sequences, right? So, we assume that the examples that come by don't even come from a fixed distribution. It's a worst case sequence of emails. Okay, so we make no distributional assumptions from analysis point of view. I mean, of course, there are also variations of this, but in the basic model, we will make no distributional assumptions. And the goal there is to minimize the number of mistakes, right? So now we cannot guarantee some sort of absolute whatever error, because the data doesn't come from a distribution, but now our goal is to minimize the number of mistakes. And in order to have any hope to do anything interesting, we'll of course also assume that the target function comes from some, again, fixed class of functions. Right? Obviously, the target function can be anything, then there is no way to minimize the number of mistakes. The adversary can somehow force you to make an unbounded number of mistakes, which would not be interesting, right? So to hope to do anything, we're going to assume that basically the target function is a simple function again. We've been assuming this throughout the course anyway, even for distributional learning scenarios. We obviously have to assume it here too. Okay, so that's the online learning model. And so right here we'll make no assumptions about, so basically we assume that the input sequence of examples is the worst case sequence of examples, and our goal now will be to minimize the number of mistakes, to bound the number of mistakes, and we'll assume somehow that the target function is nice. Okay, and I'll be very concrete today. I'm just going to focus on the case of linear separators because I want to talk about, the perceptron algorithm. Okay, And I'm going to skip this for now. If you guys are curious, you can come back to this later. So there is a motivation for that model, but let me go to linear separators. Okay, good. So just to be concrete, just to keep the flow, right? So now let's think about the case when the target function is a linear separator. So I'm in the online learning model, but the target function is a linear separator. So basically, let's assume that the Euclidean, so the instance space is a Euclidean d-dimensional space, right? And we are thinking about linear decision surfaces, like we've been seeing throughout the course, right? So basically, the hypothesis class is now the class of linear separators. And so, so the linear separator is basically given by a normal vector W and the bias W0, right? If for any example x, if W dot x plus W0 is greater than or equal to 0, you predict plus, otherwise you predict minus. So you take the sign of this quantity over here, right? So we've seen this throughout the course. Okay, cool. Now for my class today, I want to make us, because we're gonna keep the notation simple, I want to simplify things a little bit. So I want to assume that basically I have no bias. So I want to assume that my separator is what we call homogeneous linear separators. So it goes to the origin, right? So if W0 is 0, obviously, then my separator will gonna go for the origin. Oops, is this working? Yeah. So do you guys see why I can do this without loss of generality? So I claim that I can assume without loss of generality that the separator is a homogeneous linear separator. Do you guys see why? Yeah, so I can translate the origin. Okay, so that's a good explanation. And to make it 100% formal, I can always re-represent. So that's a very good explanation. But I can, just to make it 100% formal, I can re-represent the data. I can put it into d plus 1 dimensional space by adding a dummy feature that is always set to 1. And then I can argue that if the data is linearly separable by a separator that goes through the origin in this feature space, then yeah, so it's right. So the data is linearly separable by a separator that goes through the origin of this feature space, if and only if it's linearly separable in the origin space. Yeah? I mean, you can quickly verify, right? So if you see the original input feature representation, if I add a dummy feature, right, you can verify that if, right, there exists a linear separator in the original space, if and only if right, there exists a linear separator, right, a homogeneous linear separator in the new feature space. Okay, so it's very simple to argue that without loss of generality, I can assume that the separator goes through the origin. If I have an algorithm for the case when the separator goes through the origin, I can do this simple transformation, translate the origin, as you said, and I'm done. Yeah? Cool. So I'm going to assume that that's the case. And okay, so let's think about target functions that are linear separators that go through the origin. All right, and let's describe the perceptron algorithm. So as you see, it's basically the simplest algorithm you could imagine. Cool. So it's basically a greedy algorithm. So we're going to start, it's an online algorithm. We're going to go for a number of rounds, arbitrarily large number of rounds. So initially, we're going to start with so to describe my separator, all I have to describe is to describe the normal vector, right? Because now I'm seeing the, right? So when we go back to my picture, what is a normal vector is basically, right? This is my separator and this is a normal vector, right? And if the separator goes through the origin, then the only thing I need to tell you is the normal vector. Because, good? So here's the algorithm. We're going to start, so our original guess is the original normal vector is all 0, right? Okay, now we go around. And given an example x, so we have a current guess. So t here actually going to track the number of mistakes. So I'm only going to update. So this algorithm is a conservative algorithm. I'm only going to update when we make a mistake. And by t, I'm going to know the number of mistakes. So I'm going to have, at some point in time, I'm going to have wt, which t corresponds to the number of mistakes I've. Wt will be my current guess for the target, and t corresponds to the number of mistakes I've made in the past. Okay, so given an example x, I'm going to try to use my current guess for the target to predict. So I'm going to predict positive if and only if the dot product between wt and my current example x is positive. Okay, now if I make a mistake, on a mistake, I do the simplest update we can think about, right? So if we make a mistake on a positive example, that means the dot product between wt and x was negative, right? But it should have been positive. And so if we make a mistake on a positive example, then we just add that example to the current weight vector. Because if we do so, we move towards the right side a little bit, right? We are more likely to classify this current example correctly, right? And similarly, for a mistake on a negative example, we subtract that example, right? Because if it was a mistake on a negative example, that means that the dot product was positive, it should have been negative. And so that's why I subtract the example, will be more likely to be more correct on that example. Okay, the most natural, greedy approach you could think about. Cool, so that's the perceptron algorithm, and actually it's also very immediate to see, and this will be useful when we talk about kernels. Actually, given the way the algorithm operates, at any given moment in time, WT, so the current wave vector, basically it's a weighted combination. It's a linear combination of the examples on which we made mistakes, right? So for example, if all the examples that we see are different examples, right, they are all distinct, right? Then basically at any moment in time, I classify WT will basically be just a sum of the examples I've seen so far. And if the example was a negative example, this will be -1 because we subtracted that example, that mistake, right? If the mistake was a positive, if the mistake was, say this mistake was on a positive example, then this coefficient will be +1. Right? But anyway, so it's very simple to see that at any given moment in time, the current weight vector is basically just the current guess for the target WT is just a linear combination of the examples on which we made mistakes. Because we started with all zeros and we either subtracted or added an example only made a mistake. Great. And this will be important when we talk about kernels actually, because the point here is that now to make a prediction, all I need to do is to be able to compute those products between a new example and one of the mistakes I've made. Okay, so I'll come back to that either today or next class. Okay, so it turns out to be an important point. Good. So that's a perceptron algorithm. Actually, let's run it on a simple example. Okay, I came up with this example this morning, so let's hope it works. So Tom made a comment yesterday that you understand an algorithm once you see an example, so I use that comment. Okay, cool. So here's an example, a pictorial example. So let's assume that we have 6 examples, like these are the positive examples and these are the negative examples. And this is obviously on this example, the maximum margin hyperplane will be this green hyperplane. Okay, and so let's quickly run the perceptron. So initially we start with the all 0 vectors, right? This is the vector. Now let's assume that this is the very first example that we see. And if we compute it, this is a negative example. Negative example, but when we compute the dot product, because this is the all 0 vector, get it wrong, right? Because we predict positive, right? Because here we predict positive if and only if the dot product is greater than or equal to 0. So we make a mistake on this example. Now, because we make a mistake, what we're going to do, we're going to subtract the negative example from our current wave vector, which used to be all zeros, and we're going to subtract that example. And so the new weight vector will be this vector over here, which is, this is a new normal vector, the vector 1 minus 2, because it did subtract the example. So this is a new normal vector, and this is the hyperplane given by that normal vector. Okay, good. Now a new example comes in. So say that our next example, says this one, this positive example over here, right? And we see actually that this is on the right side of the hyperplane, right? This is exactly where my current wave vector predicts positive, so we're going to get it right. Okay, so and you can also compute the dot product to see that. Okay. Now let's assume that the next example that comes in is this positive example, right? So pictorially, this is on the wrong side, right? So because this weight vector, this current wave vector predicts positive on the examples that fall in this region and predicts negative there. Okay, so now this new example that comes in has a true label that is positive, but of course we don't know the label yet, right? And so we're going to use this classifier to predict the label of that example, and it's on the wrong side, so we're going to incorrectly misclassify it as negative, right? And then, so what we're going to do, then we're going to, it's a true positive example, so what we're going to do, we're now going to add to this weight vector this example, and we're going to get a new weight vector. Right? This now W3, after we added that example, will be like this. So this is our current guess for the target, and this will be the hyperplane given the classification hyperplane. Okay, and then we can keep going on. Okay, so another new example comes in, but that's a negative example. True negative example, and turns out that because this is our current guess for the target is W3 vector, and this is the corresponding hyperplane, actually W3, we're going to correctly classify this negative example, so we're not going to make a mistake, and we're not going to update our weight vector. So we are correct here, yeah? And so on. Right, I guess, let's see. So the next example that comes in is this example over here, right? So the next example that comes in is this negative example. It's actually right on the boundary. So this is my current wave vector. This is exactly right on the boundary. But when we are right on the boundary, we go by predicting positive according to our update rule. According to our prediction rule. So we're going to make a mistake on this. And so what we're going to do, we're going to subtract that example from our current weight vector. And this will be our new weight vector for the new normal vector for the hyperplane. And this will be the new hyperplane. Okay? So this is how the algorithm operates. I mean, it's really very simple. So in each round, also we have a current guess for the target. When an example comes in, we use that to predict. When we make a mistake, if it's a mistake on a positive example, we add the example to the current weight vector. If it's a mistake on the negative example, we subtract the example from the current weight vector. And we do so because if we do so, we are kind of greedily getting closer to correctly classifying the very last mistake. Yeah, so is the algorithm clear? Yeah?
So it seems like it exists some cases never converge.
So right, oops.
So how to like make this conversion stop or
Right, so in the online learning model, so that's an excellent question. What do you mean by converging, right? So in the online learning model, so there are possible many answers to your question. Like in the online learning model, we don't even care about converging. In the online learning model, as I described it, I assume that I have an arbitrary sequence, an arbitrarily chosen sequence of examples, and my job is to just use this algorithm to make a prediction every day. And my goal is to minimize the number of mistakes.
just
Minimize the number of mistakes. Yeah, now, of course, that's one answer. A different answer is I could actually also use this algorithm. So if the data is truly linearly separable, and if it has a margin, as I will describe in a second, I can actually use this algorithm to find a consistent classifier if I cycle it through the data enough times. Okay? And then I can also do, if furthermore I have a distributional assumption, if I assume that it's an online process, but if my examples happen to come from a distribution, then I can also guarantee that after not too many examples, after I see 1 over gamma squared times 1 over epsilon examples of gamma is a geometric margin, then I can guarantee that I'll get a classifier that has error at most epsilon. Okay? Now I'm assuming that the data is perfectly separable to make this statement. Now, what if there is not perfect separability? You can extend these guarantees to talk about, well, maybe there is not a perfect separator, but if somehow the number of points the total distance I have to move the points around to get them right by the right margin is small, then something nice will happen. So there are extensions, all sorts of extensions. So this has been widely studied, and there are all sorts of variations. Okay, but in the model that I'm talking about today, the way to think about it is I can go for an arbitrary large number of rounds. I get an arbitrary sequence of examples. And each day, I get an example like an email, and I have to make a prediction, spam or not spam. And then I can just get the label at the end of the day, I update it, and I keep doing the same thing next day. And I don't necessarily, in this model, I don't necessarily talk about convergence so much. All we want to do is to minimize the number of mistakes. Okay, so let's think about this today. Okay, so that's the algorithm, and right, and it turns out actually you can analyze the performance of this algorithm as a function of the geometric margin. So you can show that if the sequence of examples that we get has a large margin, large geometric margin, then the number of mistakes we're ever going to make depends just on that margin and nothing more. Okay, and now let me describe the notion of margin that Perceptron uses. Okay, so the notion of margin that Perceptron uses, I think, is arguably the most intuitive notion of margin you could think about. So it's basically just the geometric margin. So, I mean, here is a linear separator given by normal vector W, given an example X. Right, this is a correctly classified example. So it's an example that actually is positive, and given an example X that is classified as positive by my separator W, given by my linear separator given by W. Right, so basically the margin here is just the distance from the point to the hyperplane. Geometric margin, right? The distance from the point to the hyperplane. This is the margin on an example that is classified positive by my separator W. And the margin on a negative example, it's again, I guess people define it in two different ways. You can define it as being the distance or minus the distance. Okay, it doesn't really matter. It's just the absolute value of the margin is the distance from this point to the hyperplane under any definition. Okay, so the margin is very, very simple, right? That's just the geometric margin here in Euclidean space. Yeah. So this is the margin of a point. So given a separator, right? Given a linear separator specified by normal vector W, the margin of an example X with respect to that linear separator is just the distance from the point to the separator. Okay, cool. And now if I give this is for a fixed point X. Now if I'm giving a set of samples, so if I have now a training set, a fixed set of examples, then the margin of my set S with respect to a linear separator specified by normal vector W is just the minimum margin over all points x in S with respect to that separator. Just the minimum margin with respect to all points, over all points with respect to that separator. Natural, right? And now, so this is the margin, and then, so this is the margin of a set S with respect to a fixed separator. Now we can also just talk about the margin, now we can also talk about having a set S and talk about the margin of the set S. Okay, and the margin of the set S then is the maximum margin that the set S has over all possible linear separators. So it's maximum over all possible linear separators, minimum over all possible points in my set S. Yeah? It's the most natural thing you could imagine. Is this clear? Yeah? Good. All right. And now here is the interesting fact. So it turns out that we can provide a guarantee for the perceptron algorithm that depends entirely on the margin. Right? So we can argue that if the data, right? So somehow it's basically an arbitrarily chosen set of points of an arbitrary size. It can be exponential in the dimension, can be triple exponential, it can be huge, it can be actually infinite in size. Right? So arbitrary size data set, as long as it has margin gamma, so as long as there is a separator that separates the data correctly by margin gamma, I'm guaranteed that the perceptron algorithm will never going to make more than R over gamma squared mistakes, where R is the maximum length of an example. Right? So basically, if all the examples lie in a ball of radius R, right, and if the separator, if the best linear separator has margin gamma with respect to this set of training samples we're going to see, then we are guaranteed that the number of mistakes we're ever going to make is no more than R over gamma squared. So basically, what this says is the number of mistakes the perceptron makes depends entirely on the margin of the data set and nothing else. And this is true for a sequence of an arbitrary size. Okay, and just a comment here, why do we have to have this R in the bound? Well, because if we do so, I mean, obviously, kind of, if you don't want the bound, so somehow, yeah, you need to consider normalized margin, right? Because you could only scale the examples and artificially increase the margin. But the number of mistakes should be really the same, right? So this makes everything scale invariant. Okay, so I mean, it shouldn't matter if we use centimeters or meters or anything like that. Yeah, so it's very natural to have it here in the bound. Okay, so that's the guarantee for the perceptron algorithm. Okay, cool. And I do have time to actually go for the proof. And the proof is a super simple proof, a one-slide proof. Okay, well, it's insightful, but it's a one-slide proof, so I can describe it in one slide. Okay, cool. So, right, what I want to prove is that if on my set S, right, there is the separator that has margin gamma, and if all the points are inside the ball of radius R, then the perceptron algorithm is never going to make more than R over gamma squared mistakes. Yeah?
Just a quick comment. That's also assuming that it's linear separable.
I'm assuming linear separability, yes.
Okay.
Absolutely, definitely. Okay, and I don't have it on my slides. I have it on my lecture notes that I'm going to post online. Actually, if it's not linearly separable, you can still give bounds. A mistake bound that depends on the hinge loss, the average hinge loss, the total, which is intuitively speaking the number. If the data is not linearly separable by margin gamma, I make a couple of mistakes. But if the total distance I have to move the points together on the right side by the right margin, then I can still give a mistake bound that depends on that total, distance that I have to move them will be R over gamma squared plus the total distance that I have to move the points to move them on the right side by the right margin. So intuitively, if it's almost linearly separable by almost a large margin, then things are still good. Yeah, but excellent point. So I'm keeping things simple. So I'm assuming linear separability. And moreover, I'm also thinking, actually, for this to be relevant, I mean, for this to be interesting, you know, I said that the size of the set could be arbitrary in size, but I mean, for this to be interesting, I'm also thinking about gamma not being too small. Like if gamma was exponential in the dimension, then I'm going to say, I mean, I'm not going to, the number of mistakes is up with the exponential in the dimension is not too good. Right? So actually, the regime in which this behaves well is when gamma is small. Okay, and actually, there are simple examples. Again, these are examples that I present in my learning theory course. There are simple examples where the data is linearly separable, like you can have decision lists, very simple type of decision trees. So you can have a very simple example, the data is separated by a simple decision tree, but somehow the margin of the best linear separator is exponentially small in the dimension. So those are not good cases for this result. Right, so for this result, to say something interesting, we have to think about scenarios where the data is first linearly separable, as Tom is saying, and also when it moreover is separable by kind of a reasonable margin, large margin, but it's not super tiny. But there are extensions of the result, so the margin is large, but the data is not quite linearly separable, then we can extend this result. Okay, cool. So we are ready to come up with the proof of the result. Okay, so let's think about the case when the data is separable, linearly separable. The target, so there is a linear separator, but perfectly gets the data, and it does so by margin gamma, geometric margin gamma. Okay, and our update rule is actually just summarized here. When we make a mistake on a positive example, we add that positive example. If it's a mistake on a negative example, we subtract that example from our current guess for the target. Okay, so here is the proof actually. So what we're gonna show. So the main idea of the proof is to analyze two quantities. What we're going to analyze is the length of the current guess for the target. So as you saw in my example, the current guess for the target, so the length of the current guess for the target could increase, right? You saw it, it was true in the example that I showed. Okay, so the weight of WT could increase as the time goes by because we keep adding stuff to it, or subtracting stuff to it. Okay, so, right, so the key point is we're going to analyze the length of current guess for the target, and we're going to analyze its dot product to the W star. Okay, so let's fix W star to be the separator of maximum margin over the sample that gets the data right. Right, I'm going to fix that. And so in the proof, what I'm going to do, I'm going to analyze the length of the current guess for the target WT, and I'm going to analyze how the dot product between WT and W star changes. Okay, and I'm going to make my inference based on these two quantities. Okay, cool. So let's see. So the very first claim, so I have two claims. Oh yeah, and I'm also just assuming for simplicity, I can always assume, so I also assume that W star is the maximum margin separator, and I'm going to assume that the length of W star is 1. I can always, why not? It's just I can always renormalize that. Okay? So I'm going to assume that W star is of length 1. Okay, so here's the claim 1. Claim 1 will be that every time I make a mistake, so every time I have to update the separator from WT to WT plus 1, the dot product between the dot product between my current guess for the target and W star increases by at least gamma, or gamma is the margin. Okay, do you guys see why? Well, we're going to use the update rule. Yeah, every time we make a mistake on a positive example, we add that positive example to my current guess for the target. Every time I make a mistake on a negative example, I subtract my example from the current guess for the target. And moreover, I also use the fact that I know that on every single example, including that example on which I make a mistake, my W star has a large margin, has margin at least gamma. Right? So then this immediately implies this quantity over this fact over here. Is everyone happy with that? So actually, let me summarize the update rule. So another way to rewrite the update rule, oops, let me see if I can do that because I have time. Okay, so let me go here. Another way to just rewrite the update rule more succinctly, which is equivalent to be the WT plus 1 is WT plus the label of X times X, right? It's another way to write it, right? Because if I make a mistake on a negative example, I subtract the example, yeah? And so now given this fact, I can just compute WT plus 1 dot W star will be WT dot W star plus will be exactly L of X times W star dot X. But I know exactly that because I have W star as margin at least gamma, that second term is at least gamma. So immediately implies that I want. Is this clear? Okay, so let me see if I can. So right, what I'm saying is basically another way to rewrite the update rule is to say that WT plus 1. So when I make a mistake, I update the vector as follows. WT plus 1 will be WT plus the label of X times X. And so now if I go ahead and compute, okay, I'll have to erase this, but it's okay. If I go ahead and compute WT plus 1 dot X, that's exactly WT dot X plus the WT. What do I do here? Oh, sorry, this is what I'm computing. Okay, okay, that's why I was getting confused myself. Okay, what I actually have to compute is not what I need to compute. Good. I was worried for a second. Okay, so now what I have to compute, right? So this is the update rule, and what I have to compute is wt plus 1 dot w star, right? This is what I want to argue. I want to argue that when I make a mistake, the dot product between the current weight vector and w star goes up by gamma. Okay, so all I have to do, I use these two facts. I use this update rule over here, and I'm using the fact that w star has a large margin on that example. In general, has marginal least gamma on all examples. In particular, has marginal least gamma on that example x. And this is what it means to have a margin, right? Actually, oh yeah, so one thing I didn't mention actually. So the distance one, okay, maybe that was, so once we normalize w star to have length 1, then if you think about it, the distance from the example x to the separator given by w star will be exactly x to w star. Okay, if that example is positive. Yeah, so that's, I'm using this fact here. I'm using a fact about the geometric margin. Okay, maybe that's why it wasn't entirely clear, right? So actually I claim that when I talk about the geometric margin, this is exactly the margin of my example x. Okay? It's just a fact about geometry. Okay, so now given this fact, then this is the dot product between wt plus 1 and w star will be the dot product between wt and w star plus will be L of x times w star dot x, but we know that this is at least gamma. Right? So then this immediately proves claim number 1. Right? So I'm using the definition of the geometric margin of an example x with respect to a separator given by a unit length normal vector. I'm using the update rule, and I'm using the fact that my separator w star has a large margin. Okay? Just from these three facts, I immediately get this claim number 1. Okay, and I think unfortunately I have to erase this because now I have a. Okay, maybe I don't erase it. Okay, let's see. Good. So that's fact number 1. Okay, now we also, as I said, we also need to analyze the square length. We also want to analyze the length of the current guess for the target. And the claim, a second claim is that, and it's very easy to prove, is basically that every time we make a mistake, the length of our current guess for the target goes up only by r squared, or r is the maximum length for an example. It's the radius of the ball in which our points lie in. Okay, and do you guys see why that's the case? If I click, then you'll see immediately the proof. Well, so what do we do? So when we make a mistake, we update, right? How do we update? I mean, as I mentioned, we either add or subtract an example, right? This is the update rule. And so if you think about it by just using the Pythagorean theorem, how do you pronounce this, Tom? Pythagorean theorem? Okay, good. I know the Greek pronunciation, which is probably more correct anyway. So, right, so if by just using this basic Pythagorean theorem, you can just, and using the, basically you can notice, right, so what happens when you make an update, right, to add or subtract an example x, and so obviously the length, the new length squared is upper bounded by the old length squared plus r squared, or r is an upper bound on the length of x, right? So that's the geometric explanation. Okay, and now we are ready basically to piece these two facts together to come up with the final proof. So what do we get after m mistakes? If I made m mistakes, what do I know about the dot product between, right, so what do I know about after m mistakes about the dot product between the current guess for the target and w star? Is lower bounded by? So if I use claim number 1, every time I make a mistake, I add at least gamma to the dot product to the current guess to the target, right? So what do I know after the mistakes? What's the dot product between Wm plus 1 and W star? What is the lower bound? Okay, so after m mistakes, the dot product between Wm plus 1 and W star is lower bounded by gamma times m, right? Because every time I make a mistake, I add m to my dot product. So I add gamma to my dot product, right? So after a mistake, that's at least gamma times m by claim 1. And also I also know that after m mistakes, a consequence of the second claim is that the length of the current guess for the target, so the length of Wm plus 1, cannot be too large. It's only upper bounded by r times square root of m. Right? So that's a consequence of claim 2 and a little bit of manipulation. Okay? Okay, now I'm ready to piece these two things together to get my final guarantee. And the claim now is that we always have the case, it's always the case because W star itself is a unit length, so because W star itself is a unit length vector, by using the Cauchy-Schwarz inequality and also looking pictorially, you can show that the dot product between Wn plus 1 and W star is upper bounded by the length of Wn plus 1. Okay, and pictorially also you can see, let me actually erase this to be more clear. Oops. Yeah, okay, I erase everything. Good. Right, so pictorially you can also see this fact, right? So basically, this is formally follows from Cauchy-Schwarz. This is also the picture. So if I project Wn plus 1 onto W star, then it's this dot product, which is actually the projection of Wn plus 1 to W star, is upper bounded by the length of Wn plus 1. Okay, and so now using this fact and using this fact and these two claims, then we get that after m mistakes, we have a lower bound on this quantity, the dot product between Wn plus 1 and W star, which is gamma times m, and we have an upper bound on, right, we have an upper bound on the length of Wn plus 1, and so by piecing these three things together, we get that after m mistakes, we get that gamma times m is upper bounded by r times square root of m. And then if I solve for m here, just square everything, then we get that the number of mistakes is upper bounded by r over gamma squared. Okay, so that's pretty much the proof. So I mean, that, again, going back to summarizing the proof, so what the proof shows, okay, so first of all, one thing is it's not the case. Okay, what would be even nicer is if we could argue after every time I make a mistake, I get closer in angle to W star. That's not the case for this version of perceptron. There are variations of perceptron that will ensure that that's the case. For this simple version of perceptron, I just do the simplest possible update, or I add or subtract an example, a mistake, then we cannot quite argue that every time we make a mistake, we get closer in angle to W star. But what we can argue, we can argue these two facts. We can argue that every time we make a mistake, the dot product between the current wave vector and W star goes up by at least gamma, and also I'm guaranteed that the length squared of the current gas for the target doesn't go up by too much. And by using these two facts and basic geometric intuition, we can immediately come up with this upper bound on the number of mistakes that the perceptron makes as a function of the margin of the data set, geometric margin of the data set. Okay, so that's pretty much the analysis. And I guess, right, this hopefully gives you more intuition of why margin somehow is something good. Yeah, but actually, it's the simplest proof of the fact that margin in machine learning is a useful concept. And if you have margin, in this case, you don't make too many mistakes, right? This is in an online learning scenario, in a mistake-bound scenario, but then you can argue this, use this to then argue generalization guarantees if the data comes from some fixed unknown distribution. And as I mentioned, you can extend this perceptron algorithm to handle the case when the data is not quite linearly separable, but you have the so-called small hinge loss, and there are many other extensions. And more importantly, and this is what I'm going to talk about next, actually, the perceptron algorithm can be kernelized because most data is not linearly separable in the original space, but there is this interesting notion of kernels that has been very popular in the last decade in machine learning, where somehow, even if the data is not linearly separable in the original space, or that somehow maybe there is an implicit mapping to a much higher dimensional space, or the data somehow becomes linearly separable, maybe we can exploit that if we somehow have something called a kernel. Okay, but I'll talk about that next time. A very cool topic. And also just like AdaBoost and Perceptron has been well used in practice and has very nice foundations. Great. Some more questions? Yeah?
So the mistakes we just proved is the mistakes, the classifier make in the, when it is training, right? It's not the mistake of the final perception.
Yeah, so the way to think about in this online learning model, we don't even have a final classifier. We're gonna, right, it's the mistake, right, it's the number of mistakes in the past data, right? But what we are guaranteed is that if you have a large margin, no matter how many samples you're gonna see, the number of mistakes that you're ever gonna make is only upper bounded by 1 over gamma squared.
So actually,